In this video, we are going to extend our rules of differentiation. And this is a very special rule. It's something that you end up using quite a bit. And as the name suggests, it has to do with a product. Right? And what do we mean by the product rule? Well, you know, so far we know how to, as far as rules that allow us to take two functions and perform an operation on them to create a third function, we have a sum rule, we have a difference rule. But there are other ways we can take two functions and combine them. One thing that we can do is to multiply them. Hence, we need to know if we take the product of two functions that are differentiable, how do we find the derivative of that product, right? So let's go ahead and see what this rule is all about. So suppose f of x and g of x are differentiable functions, right? And we know what that means. It means that individually their graphs are nice and smooth. They don't have any holes or jumps or sharp corners or vertical asymptotes or vertical tangent lines. Nice smooth graphs. So now let y be the product of these two. So let's say we multiply them, right? So I mean, is the product also differentiable? And if so, how do we find the derivative, right? So anytime we have a question like that, whenever we encounter something new, we have to turn our attention to the limit definition, because that's really all that we know, right? So let's see what the derivative of this product looks like. So applying the limit definition to this product, in the numerator, I have to replace all the x's with x plus h. So the numerator looks like this. And then minus, I don't change this part, I just bring that down. So f of x times g of x. It's just that now we have these products here. And then this is all over h. Then the question is, like, what do we do? What do we do at this step? I don't see any common factors. I don't know, like, what is that next step? Well, in proofs and in derivations and so forth, there's always, there are always one or two steps where it's like, man, something insightful really happens here. You almost want to say some magic happens at this step, right? But it's not just pulling a rabbit out of a hat. It's thinking through it logically and then making some connections. And I think that's what really sets mathematicians apart, is that insight that they have. So the trick here is to add and subtract a special term in the numerator. So well, actually, the way I'm going to do it, I'm going to subtract a term and then add it back in to kind of balance it out, because I don't want to change the difference quotient. I just want to write it in a form that then leads me to like a next kind of important step. So what is this term? So I'm going to write down the first term that's in the numerator, the f of x plus h times g of x plus h, and then I'm going to subtract f of x plus h times g. But then I'm going to add it back in, so plus f of x plus h times g of x, and then bring down the other term that's in the numerator, so minus f of x times g of x, and this is all over h. And surely you're saying to yourself, what on earth is he doing? Why did he do that? Well, let me show you. Let me give you a glimpse into the insight. If you notice now, first of all, I have four terms in the numerator. And one of the tricks from algebra is when you have like four terms in an expression, one thing you try to do, if you need to factor, for instance, is to factor by grouping. And look, in the first two terms, I have an f of x plus h in common. I have it there, and I have it there. So I'll be able to factor that term out of the first two terms. And then look at the last two terms. They have a g of x in common. So I'll be able to, again, factor by grouping. And that's essentially what you do here, right? And that was the whole idea. You kind of think of what you need. What kind of term do I need to add and subtract in so that now I get these like terms, right? So again, that's the insight that would have been needed. Okay, so let's go ahead and do the factorization. So we have the limit as h approaches 0. So we're going to have f of x plus h. And then I'll put the remaining factor in square brackets. So what's left? I have a g of x plus h. And then minus g of x. And then close my square brackets. And do the same thing. Factor out the g of x that I have in red. So this becomes g of x. And then I have another quantity which I'll put in another pair of square brackets, f of x plus h minus f of x, close the square brackets, and this is all over h. All right. Now, here's the other thing too. Start to look for patterns as far as things that look familiar, things that have to do with derivatives. Because look at this. I have a g of x plus h minus g of x. That's the numerator in our difference quotient if I were to use the function g. And then look at this square bracket. I have a similar difference quotient, but instead it's for f. So the question is, how can I, again, use algebra to rearrange it so that I have this part over h and then also this part over h? Well, because of the property of fractions, what I am allowed to do is so let's write it like this. I'm going to take this big fraction and write it as two smaller separate fractions but with the exact same denominator, right? So I can write this as f of x plus h, and I'll put this 1 over 1 so you can see it clearly, and then times what I have in square brackets, the g of x plus h minus g of x, and then all over h, and then do the same thing with the second term, plus do g of x over 1, and then I'll have again what's in square brackets, the f of x plus h minus f of x all over h. And that is what I'm taking the limit of, right? Well, now I get to use my limit properties. So there are four ways I can sort of split this up, because here I have a product, and I know that both of these limits exist. One, because we know that g is differentiable. That was a part of our hypothesis. And I know that because f is differentiable, I know that the f function has to be continuous. That was a result we proved earlier. So, and then the same thing here. G is continuous, and also this limit, the limit of this difference quotient exists because, again, we assumed that f is differentiable. So I can take this single limit and write it as the limit of these four expressions. So the limit of f of x plus h times the limit of, as h approaches 0, of g of x plus h minus g of x all over h, and then plus the limit of g of x, and then times the limit of f of x plus h. Oh, my parentheses and stuff got mixed. So f of x plus h minus f of x all over h. right? So all this stuff, I mean, it looks messy, but we're getting to a point where now we can see the finish line, right? Again, by continuity, I can evaluate this at h equals 0. So I'm just, the first factor here is just f of x. The second factor, because we know that g is differentiable, this is g prime of x. This is the definition of g prime of x. Plus, this one now, this is the only, of the four things that I've split up, this is the only one that doesn't have an h. So as far as the limit is concerned, uh, this g of x just stays the same because there's no x that's affected by this limit, right? So it's the function itself is not a constant, but because the limit is as h approaches 0 and there is no h here, there's no change to the g of x. So the g of x comes down. And then lastly, what we have right here is again another limit definition, but this time it's for f prime of x, the derivative of f, right? And that's what we've come up with, right? So let's summarize this formula like we've done. So if y equals f of x times g of x, so if we have this product, then through our limit process, we have this formula for the derivative. And the way it worked out, the way I did the algebra, we ended up with f of x times g prime of x plus g of x times f prime of x. But there are several ways that this can be written. Because these two terms are being added, it doesn't matter if I did write this one first, followed up by this one. My personal preference is actually to start with the f prime times g. So I'm going to write that term first. So f prime of x times g of x plus, and then write this term. So f of x times g prime. Not only that, but many times, and I'll just say this before we get into a few examples, whenever I'm applying these rules, I tend not, and I recommend for you not to get fixated on the f and the g. Focus more on the operation, the fact that there's a product here, and whenever we have to find the derivative of a product, this is how I normally say it. I call this the first function simply because it's the first function in the product, and I call this the second. So the way I would read this out, I wouldn't say f and g, I would just say the derivative of this product is the derivative of the first times the second plus the first times the derivative of the second. And this is the famous product rule for derivatives, right? So this is our product rule, right? And it's very, very useful. Sometimes it's an optional rule, but other times it's a rule where you really don't have a choice. It has to be used, right? So let's look at a few examples utilizing this product rule, right? The first example that I will do is one that can be done two ways, and I want to go through both ways so you can see equivalent approaches to solving this particular problem. Okay? So I'll just write down the function. So let's say the function is 3x squared minus 4 and then times 5x plus 7. So let's say this is the product, right? So we can see the two functions. And I will refer to the 3x squared minus 4 as the first function, and then the 5x plus 7 as the second function. I am not going to just state it like just f and g. The f and g are really just placeholders. That's all it is, right? You look at different resources, different textbooks, different websites, different videos. They all use different letters. Some use f and g. Some use u and v. Some use u and w. It's just the list goes on, and it has nothing to do with f and g, but in fact it has to do with the fact that there's a product here. And whenever we're differentiating a product, like we have right here, the product rule applies. So since this is the latest of our rules, hot off the presses, let's go ahead and apply it. And then after that, we will solve the same problem, but in the alternative way. All right. So again, I'm going to refer to this. Let me write it there so you'll see it. So I'm going to refer to this as the first function, and I'm going to refer to this as the second function. All right. So let's write down what the derivative is. So the derivative of y with respect to x is, so the derivative of the first is 6x. When I just look at what I have in the first pair of parentheses, if I differentiate that, I'll get 6x. But then the product rule says I have to take that 6x and multiply the second function. And then I need to add to that the first function, so that quantity, 3x squared minus 4, times the derivative of the second. Well, when I differentiate this linear function, I'm just going to get 5 plus 0, right? Because of our constant rule. So we're just going to have a 5 there. So that's the derivative, right? It's not necessarily simplified, but we can do that. Now let's distribute the 6x. So we will have 30x squared plus 42x, and then plus 15x squared, and then finally a minus 20. All right? So we have a pair of like terms. So 30x squared plus 15x squared is 45x squared. And then there's only one term with an x, so bring it down. And then there's just one constant, bring that down. And that's the derivative of our product. Right? Now, I mentioned earlier that there's an alternative way that we could do this. The alternative way, since we have a fairly simple, we have two binomials, what we could do is we could FOIL out the binomials. That way we would get rid of the product and we would just have the sum or difference of terms, right? Which we can differentiate without using the product rule. So here's an OR, as in we could do this or we can do this, right? So let's first rewrite the function. So let's FOIL out and see what we get. So we have, this would be 15x cubed, and then a 21x squared, and then a minus 20x, and then a minus 28, right? And so we FOIL it out, and look, no like terms here at all. But the important thing about this is that we now can differentiate term by term. We've essentially gotten rid of this product of the two functions, and we've replaced it with just, the sum and difference of these terms. So let's write down the derivative. So using the power rule on the first term, bring down the 3, multiply the 15. So that's 45x to the, and then subtract 1 from the power, x squared. The derivative of the second term, bring the 2 down, multiply the 21. So that's 42x to the 2 minus 1, so the first power. And here, remember, this is that special case of the power rule. It's not 0 just yet. I'm a little preemptive there. Come on, there we go. So this is to the power 1. Bring down the 1, multiply the negative 20. So this will be negative 20. And then you'll have x to the 0th power, which is 1. So take a look at it. Same derivative, different process, right? And that's the thing about differentiation. You have lots of ways of, I wouldn't say lots, but usually several ways that some of these problems could be set up. And here, because we're working with, two basic polynomials, that it's relatively easy to go ahead and FOIL them out. We could rewrite the function, apply a slightly different set of rules, right? And then end up with the same result, right? So our first example there, we had a choice. Now let me show an example where we don't have a choice. So, or even if we FOIL things out, we're still going to end up having to do the product rule, right? So here's this function. Let's say we have e to the x plus x, and then we have the quantity, the cube root of x minus 2x, right? And what's going to happen is, let me FOIL it out anyway so you could see, right? So I'm not going to take it any further, but I'm just going to do the algebra just to show you what the difference is in this problem compared to our previous problem. If we FOIL things out, we would have e to the x times the cube root of x, and then minus, if I take the e to the x and multiply this negative 2x, I will get negative, I'll put the negative 2x first, and then I'll have the e to the x, right? And then if I distribute the x times the cube root, then it will be plus x times the cube root of x, and then finally x times negative 2x, so this is minus 2x squared. Now, these two terms are fairly easy. Like this I can differentiate. This, if I use my properties of exponents, I can write this as x to the 1 times x to the 1/3, and then add those exponents to get x to the 4/3, right? So again, I can express this term as a single power of x. But the problem now is here, I still have the product of two functions. I have the 2x times the e to the x, and there's nothing I can do to simplify this. Similarly, I have e to the x, and even if I rewrite this as x to the 1/3, there is no property of exponents that allows me to combine these two factors into essentially just a monomial, really. So I can't simplify this anymore. So because of this product and because of this product, I would still have to use the product rule. So I don't really gain anything, unlike the first example, that when we FOIL it out, we simply were left with powers of x. The e to the x cannot be combined into one of our power functions, right? So because of that, I'm not going to FOIL it out. I mean, I did, but I'm not going to use this as a way of solving the problem. I'm just going to leave the function as it is and use our product rule. Again, I am going to treat this is the first, and then this is the second, right? Now, if you want to rewrite the second one, the second function here, before we do our derivative, you're certainly entitled to do that, and it will look like this. Again, your cube root is x to the 1/3, and then you have your minus 2x, right? And I have enough rules to differentiate this by itself, and I have enough rules to differentiate this by itself, and now I have the product rule to tell me how to put those two pieces together, right? So again, what I will do, So our dy dx, our product rule says take the derivative of the first, so e to the x plus x, and then times the second, which is your x to the 1/3 minus 2x, and then add to that the first, which is e to the x plus x, times the derivative of the second, which is the x to the 1/3 minus 2x, right? So once we evaluate this or simplify this expression by taking the derivative of e to the x plus x, and similarly once we take the derivative of x to the 1/3 minus 2x, the calculus part is done, and then we have to decide how much more algebra do we want to do, right? Well, let's do the differentiation. So we know that the derivative of e to the x is e to the x, and I know that the derivative of x to the first power, when I bring down the 1, I'll get a 1, and then x to the 0 is 1. Now, because this is still a binomial, and it's multiplying another binomial, I better put parentheses there. Otherwise, I would be indicating an incorrect order of operations, right? And then plus e to the x plus x. So again, I'll keep that as a quantity. And then now we have to write down the derivative of the x to the 1/3 minus 2x. Now using our power rule, right, we will have 1/3 x to the negative 2/3, right, when I subtract 1 from the 1/3 exponent. And again, use that same special case of the power rule, x to the first power, bring down the 1, so you'll have minus 2, and then times x to the 0, which is 1. So that's the derivative. Do I need to FOIL this out? Technically, no. I mean, if the main purpose of the question is to see whether or not you can compute a derivative, you've computed the derivative, right? And now, there are things we could do. We could rewrite this so that we don't have a negative exponent. We could FOIL things out, but we're not going to get a whole bunch of like terms that we can simplify. The answer is not going to work out to be as nicely as it did in our previous example. And sometimes we just have to live with a messy derivative. And in this case, this is where I'm going to stop, right? So unless I am told specifically to simplify your answer, write your answer in the most simplified form, but even that is still a little ambiguous, because what one person thinks is simplified, someone else might think otherwise, right? So in this case, we'll stop here, and this is our derivative of this product, right? So the product rule is again another huge step forward, because there's so many functions that are expressed as the product of two or even more functions, and now the product rule gives us a way of finding their derivative. See you in the next video.